First of all, just think of a row of dominoes. So all in a line. If you tip one, it'll hit the next, it'll hit the next, and that will continue going on and on and on until time ends. You'll just continue. If we have an infinite number of dominoes. And now think about a ladder going up, and there are an infinite number of steps. So you take one step and then one more, and then one more, and then one more. And you'll get to every single step in that ladder eventually. That is the basic premise of induction, mathematical induction. So first of all, we have to figure out some sort of a statement that we're trying to prove. That for all natural numbers, or positive integers, we're going to start with 1. So 1, 2, 3, 4, 5, all of that. So for every number, there is associated with that number something that we're trying to prove. The basis step says, if I let n be 1, is my statement true? Usually that's very easy to prove. Sometimes we'll need to prove more than just one basis step. But I think the examples that we're covering, we will not need that. The induction hypothesis is the second step. Let n be k for some k greater than 1. So for some integer greater than 1, assume P of k is true. Then the induction step is use what we just did, the assumption, to show that the next step follows. And the easiest way to show you how this works is to look at a very simple example. If we have 1 plus 3 plus 5 plus all the way up to 2n minus 1 equals n squared, then my P sub n statement is that 1 plus, let's write it this way, the sum of all i's as I runs from 1 to 2n minus 1 is equal to n squared. And if you haven't seen this notation before, this bottom part is called the index. The value is the starting value. The top value is the ending value. And then we've got some kind of rule. So in our example, the rule is just I. And this notation is called sigma or summation. So the sum as I runs from 1 to 2n minus, oh, let's just do it. The sum as I runs from 1 to n of I is just 1 plus 2 plus 3 plus, we're going to add 1 and add 1 and add. We're just adding all of these numbers. Plus dot, 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 plus, and then we'll have n minus 1 plus n. So this notation is called summation notation. And it enables us to write a sum in a very compact way. And we can think of this as a rule. So in our case, we do just have I as the rule because we've got 1. Oh, I see. We're not looking at 1 plus 2 plus 3 plus 4 plus 5. We're looking at 1 plus 3 plus 5 plus dot, dot, dot plus 2n minus 1. Oh, okay. That's cool. So if I look at the number 1, that's the first number. I can think of 1 as 2 times 0 plus 1. And I can think of 3 as 2 times 1 plus 1. And 5 as 2 times 2 plus 1. And so the highest number, 2n minus 1, will be represented by n. So we are looking at a rule that looks like 2i plus 1. We're starting at I equals 0, and we're going until I equals n. So we would say our rule that we're trying to show, we want to show that P sub n is true for all n in the positive integers and the positive integers are just the counting numbers or the natural numbers. So we want to show that P sub n is true for all n in Z plus, all positive integers, where P sub n is equal to the sum is I runs from 0 to n Oh, I see. If I runs from 1 to n, because instead of looking at 1 as I see what they did. So you can express 1 as 2 times 0 plus 1. You can also express 1 as 2 times 1 minus 1. And then 2 will be 2 times 2 minus 1. I mean 3, pardon me. Then 5 will be 2 times 3 minus 1, and etc. So now we can write our statement as starting at 1 rather than 0. And we want to show that the sum is I goes from 1 to n of 2i minus 1. We want to show that's equal to n squared. So let's see. This is kind of fun. So the first thing is to show first. We've already got the rule, and most of the time they will give you the rule. So the first step is the basis step. And we're going to let n in this rule equal 1. So let's see. I need to show that P of 1 is true. We want to show that P of 1 is true. Let's see, P of 1. Here's my P of n. P of 1. Yeah, I equals 1 up to n. Oh, but n is 1 of 2i minus 1. And I need to show, does that equal 1 squared? Well, let's see. The sum as I goes from 1 to 1 is just 2 times 1 minus 1. 2 times 1 minus 1 is 1, and 1 squared is 1. So the basis step works. So basis step works. And this is like the first domino, or making sure that your ladder has a first step. Now we're going to have what's called the induction hypothesis. We're going to let n equal k for some integer k greater than 1. And we want to assume that P of k is true. P of k. I need to write it out because that's confusing to me. So P of k means I'm going to replace n's with k's. So let's see. P of k would be the sum as I goes from 1 to k 2i minus 1. And we want to, we're assuming that this does in fact equal k squared. So this statement is our induction hypothesis. We assume that this step is true, and then we want to show the induction step is that we want to show that P of K being true implies that P of K plus 1 is true. And if we can do that, then what we're saying is the bottom rung works if we assume that some other rung works, and that leads to the step above it working, then it's going to work forever for any positive input. Well, it'll help us to write what P of K plus 1 looks like. So let's P K plus 1. Well, we're going to use this rule again. And we're going to replace n with k plus 1s. So we've got the sum as I goes from 1 to k plus 1 of 2i minus 1. We want to show that that equals k plus 1 squared. And to do this, we need to use our induction hypothesis. So almost always there's a little trick to these. This time the trick is not as, somebody's walking along and all of a sudden they know the tangent of an angle that is the inverse of something. This is not that crazy. But if the sum as I goes from 1 to k plus 1 is just a list of numbers, and we're going to end with I is equal to k plus 1, I can write that as the sum of the first k numbers plus the k plus first one. 2 times k plus 1 minus 1. Does that make sense? So I've got the first k written using the sigma notation, and then plus the last one, plus 2 times k plus 1 minus 1. And what's groovy about this is that we have assumed something about this first sum. We assumed that that first sum is equal to k squared. So let's see, k squared plus 2 times k plus 1 minus 1. Well, what in the heck? But let's go back and look at what are we trying to show? We want to show that the k plus first step, this mess, is equal to k plus 1 quantity squared. K plus 1 quantity squared. Let's go ahead and multiply that out. That'll be k squared plus 2 times k plus 1. And I'm just using the rule a plus b squared is a squared plus 2ab plus b squared. And even though you can prove this using FOIL or multiplying it out, this is a really handy thing to have in your head. So we've expanded this binomial. We've got k squared plus 2k plus 1. Oh, okay, I get it. If I can get k squared plus 2k plus 1 over on this bit, then I can finally say, and that is k plus 1 quantity squared. I think we can do that. Let's see. So we've got k squared, and then we're going to distribute the 2. I'll make it look really obvious. So that's k squared plus 2k, and then 2 minus 1 is plus 1. And you can see that's exactly what we needed. And that's the proof. QED stands for quod erat demonstratum. What we have, let's see, what we have tried to prove is proved. So what is needed is shown. This is the to be verb, and it's the past tense, and this is demonstration, but it's not literal. Anyway, quod erat demonstratum is often used at the end of a proof, QED. Let's try something more exciting. Let's prove that one over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5, all the way up to 1 over n times n plus 1. We want to show that that whole thing is equal to n over n plus 1. The first step, so the 0th step, because we always, it helps to think of the basis step as step 1. The 0th step is writing 1 over 1 times 2, 1 over 2 times 3, 1 over n times n plus 1 in sigma notation. So summation notation. So I'm going to think of i's. If I have I times I plus 1, then I could start with I is 1, and I'll go all the way up to, oh, okay, groovy. I'll go all the way up to I equals n. So we're going to add these, and we want to show that this is equal to n over n plus 1. So here is the rule we are trying to prove. And even though this rule might look more complicated than the original written out, it's a very useful complicated form. We can manipulate it very, very easily. Alrighty. So basis steps. We're going to let n equal 1, and we want to show we're calling this P of n. We want to show P of 1 is true. Well, let's see, P of 1. I'm going to replace all of the n's with 1s. I equals 1 to 1. 1 over I times I plus 1. And we want that to be the same as 1 over 1 plus 1. And 1 over 1 plus 1 is just 1/2. So we want to show that if we have one term, if we have 1 times 1 plus 1, we're filling in, for I, we're filling in 1. Well, this is equal to 1 over 1 times 2, and that is equal to 1/2, which is what we wanted. So we've done the basis step. We've shown that if n is equal to 1, the proposition, the rule works. Now we do the induction hypothesis. We let n equal k for some positive integer k, where k is bigger than 1. And we're going to assume that if we take our rule and change all of the n's to k's, we're sure so that P of k is true, and P of k, let's see, we've got 1 over I times I plus 1. That's not going to change. The only things that will change are the things with n's. So this summation is going to go from I equals 1 up to k. And we are assuming that that sum is going to be k over k plus 1. Now we need to use this induction hypothesis to show the induction step. So there's the induction hypothesis, the induction step. says we want to show that P of K plus 1 is true. And when P of K is true. When P of K is true. So we want to show that if we start at any step along the way, that we can get from that step to the next one. And then we've done it. It's kind of an amazing sort of thing. All right, so we've got P of K written down. Let's write down P of K plus 1. It's P of K plus 1. It'll be the sum as I goes from 1 to K plus 1 of 1 over I times I plus 1. Because it's the same rule that we had before. It's this same rule. And we're saying that we want to show that equals K plus 1 divided by K plus 1 plus 1. So P of K plus 1 is the sum of the first K plus 1 integers plugged into this rule. So 1 over 1 plus 2 plus 1 over 2 times 3 plus 1 over 3 times 4, all the way up to K plus 1. We want to show that that really does equal. Let's write this more simple. Let's see, that's K plus 1 over K plus 2. Well, that looks better. We're going to do the same trick. We're going to rewrite this summation as the sum as I runs from 1 to K, 1 over I times I plus 1, plus 1 over, let's see, at the K plus first one, we'll have 1 over, this will be K plus 1, and this will be K plus 2, K plus 1 plus 1. So this term right here is the K plus first term. So we've got kind of a compact way of writing it using the induction hypothesis. Okay. Well, I know by assumption that this first summation is equal to K over K plus 1. And we're adding, let's just use 1 over K plus 1 times K plus 2. Well, I know about fractions. In order to add them, the denominators need to match. So I'm going to multiply K over K plus 1 by this second factor, K plus 2 over K plus 2, so that the denominator becomes the same. And the numerator, let's see, it's going to be K squared plus 2K. And I've got that just by distributing. Now we can add, so we've got plus 1 over k plus 1 times k plus 2. Well, this is easy now. The numerator is k squared plus 2k plus 1. And the denominator is still k plus 1 times k plus 2. Oh, hey, notice that the 3 terms in the numerator are a perfect trinomial squared. So that's going to look like k plus 1 all squared, because we've got k squared plus 2 times k times 1, that's 2k, plus 1 squared, which is 1. And the denominator still stays. One of the k plus 1 factors in the numerator divides out with the denominator. And we're left with, we have 1 k plus 1 left in the numerator. And we have a k plus 2 left in the denominator. And check it out. That's exactly what we needed to show. So, quod erat instruct. Do y'all have any questions? Thanks, Edgar. So I'm going to do a little bit on Wednesday. We're going to look at the Fibonacci sequence. And see what we can see. I think that that's not spelled correctly. See what we can see using induction and the Fibonacci sequence. So I hope that that will be fun for you. Again, Wednesday's class, and I need to send everybody an email. Wednesday's class will be applications of dot and cross products. Wednesday. Today is the 6th. Okay. Is today really the 6th or the, oh, it's 6. Okay. So this is 8 now. We're going to look at applications of dot and cross products. We're going to look at the Fibonacci sequence. I can't tell. 1B or 2B's, one of those is right. Fibonacci sequence. With mathematical induction. And I will answer any questions you have. Over the practice final. On the final, on the actual final, I will put an induction proof as extra credit. So the actual final will include amount, amount. Induction proof. For extra pay. All right, I'm going to send this information out as an email as soon as our class is over. Do y'all have any questions? Thanks, Edgar. Oh, thanks. Thanks very much. So I hope y'all have a wonderful couple of days. I hope finals go well for y'all. And I will see you. If I don't see you here, then I will certainly record it, and there'll be a short video for Wednesday. Bye.